a single misconfiguration exposed data from over 100 million people. This is Capital One data breach and how it happened. To understand this, we need a quick background on how cloud storage works. Capital One was using Amazon Web Services as their cloud provider. One of the main services they really used was S3, a simple storage service. S3 stores data in something called buckets. You can think of a bucket as a container that holds all files and folders of customer with sensitive data. Capital One had fully moved from traditional data centers to the cloud. This made things scalable and efficient, right? But also introduced new risks. On the day of the incident, attacker found a misconfigured web application firewall on a cloud server. By using this weakness, attacker performed a SSRF attack, that is server-side request forgery. This allowed attacker to send requests from server itself to an internal AWS metadata. That metadata service returned temporary IAM role to an attacker that holds and credentials to access those S3 bucket. By using those credentials, attacker access S3 bucket containing sensitive data, including names, addresses, and credit information of the people. In the end, this was a single misconfiguration, not a zero-day exploit or a brute force attack. Not only the Capital One breach, let me show you three other examples for cloud breaches. Tesla cloud breach, which was held in 2018. Engineers left their Kubernetes AWS console with no password. Attacker used it to mine cryptocurrency for months, and no one noticed until a routine security scan. Next, Uber 2016. A developer accidentally pushed AWS credentials to public GitHub repository. Attackers used those keys to access data of 57 million users. Uber even paid around 93 lakhs and kept it secret for a year. And another example, MongoDB 2017. Thousands of databases were deployed with no authentication. In a single weekend, around 28,000 databases were wiped and held for ransomware. These data breaches are common because of misconfiguration in infrastructure. Before I show you the problem with the existing tools, let me clearly explain what we are actually scanning. Most companies today don't click through the AWS console to configure their infrastructure as code. Instead of that, they write a simple code that describes the infrastructure, what servers they want actually, like what databases, what network rules, and what permissions they actually need. Just like an application code that contains main, variable, and state file that plugins with cloud providers like Google Cloud, Azure, AWS, Oracle, etc. The most popular tool that's let you to build, change version cloud on on-prem resources safely and efficiently is Terraform that supports multi-cloud. And let me show you the example for configuring S3 bucket on AWS. This block tells you that the resource is based on AWS S3 bucket, which contains customer data. This tells you the bucket name, prod, customer database, backup. Here is an important line. This line means anyone on the internet can read anything inside this bucket. Here is a problem, like to a new developer who just joined the team. This looks like a normal configuration. The syntax is valid, right? Terraform will apply it without complaint. It will become a real infrastructure in your AWS environment. And now there are tools designed to catch exactly these kind of issues. One of the most popular one is Checkov by Bridge Crew, used by a lot of DevSecOps teams. Not only this, to scan infrastructure, tools like Trivi, TFScan, and etc. are used to scan IAC files. So now let's try it with Checkov. I installed it earlier. Let's run it on vulnerable file. My suggestion is used to Python version 3.11 or 10 because it makes some errors on updated version with Checkov. So use Python version 11 or 10. Let's scan it on vulnerable file. Yeah, the results are started flooding. Yeah, line after line, alerts after alert. This is just a sample example file that contains only 15 resources of Terraform. And yeah, fail checks are about 43. But not all of these are real problems. Some of them are false positives, right? For example, Checkov flags missing versioning on a bucket that only stores temporary files, or it flags open ports like this that the application actually needs to work. It even flags missing encryption on a development database with no real data. So what happens next? A new developer opens the list, spends an hour spending on about how these configurations happen, and closes a bunch of false positives and fixes a few real issues and then move on. What's the real problem? Some critical issues are still there, hidden in the noise. This is what we called as alert fatigue. People tasked with responding to them leading to missed or ignored alerts or delayed response. And it honestly not about the tools issue, but it about rule-based scanners issue. They don't understand context, right? And they don't know what actually really matters. Let me show you what actually happened in real teams. The scanner runs and it generates alerts. The security team open tickets and spending hours to find misconfiguration, and false positive get closed and the real issue get missed, maybe sometimes, and even eventually it happens breaches, and these are the effects of alert fatigue. So that's the problem, right? I built something to stop this called TerraSecure, not by adding more rules, by being smarter about which rules actually matter, and by explaining why in language that developers and security teams can act on. TerraSecure has three layers that work together. Let me show you those three layers. Yeah, the first layer is about rule engine, and the second layer is about ML model, and the third layer is about AI explanations. Let me break down this from architecture of TerraSecure. Yeah, here is a layer 1 of rule engine. 50 plus security patterns that I actually uploaded about those AWS resources from Terraform file. Similar to what Checkov does, as S3 security rules, IAM, and permissions. And for each resources, I actually uploaded 50 plus security rules. And then this is a baseline. It catches known bad configurations. And the next is layer 2 ML model, an XGBoost model. I trained about 265 samples derived from real data breaches. The model extracts 50 security features from each Terraform. Yeah, I will show you the extractor. Yeah, here are the 50 plus extractor that it will extract these 50 plus resources from the Terraform file. Yeah, and each Terraform resources and outputs gives a risk score between 0 to 1.0. That means it will be exploitable. One means almost certainly misconfigured. This helps tools to prioritize instead of treating all the findings equally into prioritize the misconfigurations by risk scores like 95%, 86%, etc. And the third layer is about AI explanations. Every findings gets sent to Claude 3 Haiku running on AWS environment via Bedrock service. Claude just generate four things mainly, like what the issue actually means and what the business impact is, and how a real issue, like how a real attacker would exploit it, and the remediations, like how the misconfiguration code will be fixed. At simply, we can say that rule engine tells you what, and ML model tells you how bad it configured, and LLM tells why it matters. Let me run TerraSecure on the exact file that we just on Checkov. Yeah, a single line command that actually checks the vulnerable Terraform file. Yeah, here we are using AWS Bedrock, Claude 3 Haiku. Initially, yeah, it just generated the findings of what actually matters and why it happened and how to fix it. Yeah, let me show you the real issue was total resource 19 scanned, that shows actually 43, and issues are 12 with critical, high, medium, and detailed findings. The exact misconfiguration from capital on breach was actually a misconfigured S3 bucket. Yeah, this is one. This is the exact file that actually misconfigured by Capital One breach, named customer data. Actually, it's about ML risks about 83% critical. The explanation tells you why it matters. This S3 bucket is confirmed with public access, public read, allowing anyone on the internet to discover and potentially access its contents. The bucket name was suggest it may contain sensitive data that should be restricted. That could be easy to understand as a new developer to understand why it matters and the business impact is actually public three leading cause of Claude data breaches, explore data theft, affecting customer privacy, regulator, blah blah blah, and the attack scenario, which is mainly important to know about the attack scenario, how it would be exploitable. Like a real world example, it shows like Capital One breach exploits 100 million records, misconfigured S3 costing $190 million. Yeah, here are the detail fix. Change ACL to private from ACL public read to ACL private. This will changes the reading of public S3 bucket and enable server-side encryption. We want to encrypt those data in S3 bucket by using AES algorithm and block all the public access from environment. Let me show you the difference between the existing tools and the TerraSecure. Yeah, here we go. Here are the leading tools like Checkov and Trivi and how it works, like false positive detection method is accuracy. It is a comparison tabular column with ML model and AI. We just used can achieve more accuracy than Checkov and Trivi. And with false positives, we achieve actually 10.71%. Wait, I will show you the difference in context. Yeah, this issue is about 83% from ML risks. Confidence is about 83%. What that means is actually based on the pattern learned from the real world breaches, this configuration is almost certainly exploitable. Look at the impact section. GDPR fines up to 20 million euros or 4% of annual revenue. That's not something I wrote manually actually. That's AI generating it in real time based on the context of the issue from AWS Bedrock through Claude 3 Haiku. And look at the attack scenario section. It connects this issue directly to a real world breach. Capital One 2019, 100 million records exposed. The same breach we discussed earlier. So instead of just showing warning and documents to read those misconfiguration and fixes, TerraSecure shows you the real world consequences. Yeah, that's the different. I don't want this to feel just like a demo. I want to back it up with the idea. The machine learning model in TerraSecure achieves about 92.45%. And for comparison, tools like Checkov have around 15% false positives, but we have only 10.71. That might sound small, but at scale, it's huge. If I run 1,000 scans a month with 100 issues each, Checkov would generate around 50,000 false positives. TerraSecure reduces that to about 10,000. That's over 4,000 fewer false positives every month, which means huge hundreds of hours saved from battle prioritization. And I'm actually planning to create a playlist about this project. Before we close, let me quickly show you what this full series actually covers. I just actually posted this about this project. Episode 1 is this video, real world breaches and the problem that we are actually faced with the existing tools. And the next video will be about an end-to-end full deployment. And the third video is about how I built the machine learning dataset from real breaches, including feature extraction and data labeling. And the fourth video is about training the XGBoost model, cross validation, future importance, and how I reached 92% accuracy. And the fifth video is about how the security patterns works and HCL parsing and how rules and ML work together, the rule engine. And the episode sixth video will be AWS Bedrock integration. It's about catching prompts and reducing costs. And the seventh video will be a prompt engineering deep dive. What worked, what didn't, and where the model failed. And the eighth video will be a SARIF output and a GitHub security tab integration, turning findings into real world scanning alerts. And the ninth video will be publishing TerraSecure as a GitHub Marketplace Action. I actually published in a GitHub Marketplace package. You will get that whole package in there, Marketplace. Yeah, and the episode, yeah, 10th video will be testing CI/CD and future plan is actually. One more thing before we close, why did I build this actually? It's about, yeah, this page. When I was first read about the Capital One breach, I kept wondering there are scanners, so why didn't they catch it? But I looked deeper, I realized they don't catch it. The rule was there, it was in the report, but it was buried. Among 100 plus alerts treated as the same as small issues with no explanations of why it actually matters. That's why I can't read from them. What if the scanner was smarter? What if it could learn from real breaches, prioritize what actually matters, and explaining it in a way that makes people pay attention? That's idea become TerraSecure, and this series is how I built. In next episode, I will show TerraSecure running end-to-end with the full pipeline, the GitHub action, and the SARIF output in the security tab.